So paper we're working on, or what we did, was self-improving transformers overcome easy to hard length generalization challenges. So basically, the premise of this paper is we're going to start with some pretty simple problems. We'll get into that, just like addition, multiplication. And we start with the model that's only capable of doing very simple addition, multiplication, like very simple length. And through iterative training, we're kind of trying to generalize the model to longer lengths. So we'll start off with kind of just the problems that we're going to be dealing with. So, and I'll talk about kind of the difficulty of them as well. So we're going to be doing addition, just simple addition. That's not right, I don't think, but so English isn't my first language, so if I spell stuff wrong. So we're doing simple addition. So for instance, we could just do 12 plus 34, and then this will come in later. The difficulty of addition is just a measurement of how many digits we have. So this could just be numerically seen as a difficulty of 4 or a difficulty of 2, depending on how you look at it. We also have reverse addition. Same premise here. The only thing is we're just listing the least significant digit first. So it's just kind of a swap in that sense. It works the exact same way, like when it comes to difficulty, it's measured the same way. The reason why they talk about this, they also reference another paper in the paper. Doing length generalization on reverse addition is quicker and more efficient than just regular addition. They didn't say why or anything, but they cited a paper, so yeah. What else we'll be working on is multiplication. So this also kind of the same thing with our difficulty just being the length of the digits. And then we have maze solving. So just laying out the problems before we get into it. The difficulty will be measured by the number of nodes, as well as the length of the optimal path or the solution. So that's maze solving. I don't think I missed. Oh, I did strings. So we're also going to be doing string copy. So I'll write it down. Measurement of this difficulty is quite easy, just length of the string. And then we do string reverse as well. Do we? No, I don't think so. So yeah, string copy and string reverse. And string reverse. Okay. So here's the problems that we're going to be dealing with. And then now I'll just kind of get into the simple definitions. So this paper is a very empirical paper. So you'll see we'll kind of just do some quick definitions and just go right into the results. So what this paper is going to be doing is I'll show you guys how our data is set up. So our D0, YI, this should all ring a bell as usual. 0, 1. But the special part of this paper here is where difficulty of our xi is less than or equal to some D0. Now, this is of course dependent on the actual problem you're working with. So for our additions and our reverse and stuff, this is just like the length of our input. With maze solving, again, it's just this down here. So this is kind of like our max difficulty metric. So you can see I've subscript this with subscript 0. So this is kind of our starting data set on our easiest difficulty. And then we'll kind of work on top of that. Okay, so now let's get into the actual meats and bones and fun of this paper here. So I don't think I need to have these up here anymore. So now we'll get into the self-improving framework. That is the important part. So, okay, so a few steps here. So first thing we want to do on our model is just train on this initial data set. Makes sense, right? So first thing we're going to want to do, or they do, is train on D0. Just to start with, and then after that, we're going to do the actual self-improvement framework. So They do it on a round base, so I should probably say this before I actually write it down. So for each round, we just incrementally increase the difficulty. So if we just do a for loop over our rounds, and then here comes the fun part. So we increase our round, which is just equivalent to saying we just go up the difficulty level. And then what we do is we use the model that we've generated here, so we can just call this M0. So this is what we get from that initial data set. And then we're gonna use this model to label or categorize our following data set. So for instance, next one would be D1. So that's an increase of difficulty, just like the second digit or the third digit. We're going to train our model to see what its expected output is for each one. So for instance, let's say our D0 is trained on digits of like 2 in addition. So it, with relative certainty, can do that problem. On our D3, we would have something like 1, 2, 3 plus. So we're moving up the difficulty. So at this third step here, what we're doing is we're asking the model for what it thinks this result should be. And we're taking that result as truth. So there's some interesting things that come into that. We have a little bit of cascading errors and stuff like that that we'll get into. But we take the result of what the model outputs, so what M0 tells us this result's gonna be. And then in the next round, we train on that data set, and then we use this to keep iteratively training. We keep increasing difficulty one by one by asking the model, hey, this thing's only a little bit harder. What do you think the result should be? And then we say, okay, we think that's the result. Of course, it's not always the result, but we think that's the result, and then we just keep training as that being the truth.
Wait, so the original data set has like true correct labels YI for like the easy problems?
Yeah, it has 100% truth. It is, everything's correct.
And then everything afterwards is labeled by the crappy models that we have?
Ding, ding, ding. So,
wonderful.
Yes, so this leads to something we'll talk about, like an error avalanche, which is just our cascading error. There is ways that they mitigate the problem that it seems pretty obvious of saying a bad model, we can't take it to be a truth. We get into like data filtering techniques, which they do show works quite well. So we'll get to that pretty soon. It's pretty sure the next time we're going to talk about. But yeah, so we increase the difficulty, and then I'm just going to write down exactly what I said. Using R-1, we generate NR samples, and then now we have this new data set. So, kind of just formalizing. I should write it small. Kind of just formalize what I was saying here. We're just, our labels are being assigned by the model, right?
Mm-hmm.
And wait,
yeah.
Where is XI coming? XI is the same set of XI that was in D0, or it's a different set?
So this XI is going to be the same set with an addition of more difficult problems. So it's an inclusion of all the data sets before, but we keep incrementing the difficulty and we add new inputs for the model as we go up in difficulty.
Okay. So it's basically your indexing is like, I goes from 1 to NR, and it's indexing the same data, except that like in the R's round, the difficulty level of the examples generated is R or something.
Yes, exactly, and then we keep kind of adding from that.
You're just like adding to what existed before.
Yes.
Okay.
So yeah, so this is kind of the incremental difficulty step, and then now we, here is what we were just talking about. So now we train on D1, and then uni. I'm gonna write this fully out even though I only have one. So then now this is just an amalgamation of all the data sets that like came before that we were trained on, including our absolute truth. One thing they do here is and this also can lead to some error, is the most recent data set, or the most difficult part of the data set, it gets sampled at 50% compared to all the rest. So we have a preference to train on the most difficult part of the data set, and then, so this gets sampled at 50% of like our training set, and then these just get sampled uniform random for the rest of the 50%.
So this is somehow like modeling this weird setting where you have a bunch of XY pairs for really easy problems, but then for harder problems you have the X's but not the answers.
Well, yeah, because it's pretty easy to make a harder addition problem, just add more digits.
Yeah.
But it's not easy to do the answers. So yes, but it only really works in that case.
Except that it's easy in this case, but I think that they want to think about, okay, like you're solving math problems and they're getting gradually more difficult, and you want to get into the realm where the problems do not have the correct solutions, and somehow that's a setting that they are interested in.
Yeah, exactly.
That you kind of like seeding the model with some supervised data, but you don't have target labels for a lot of other things, and then you want to see some consistent extension of the capabilities of the model to data beyond what it was shown, whether beyond this kind of in terms of this difficulty, which is whatever it is.
Yeah, exactly. And the one point that they make as well, it's really important that our D0 is right, because if it isn't, it can cascade pretty fast. Where the paper does show there is some resilience in like memorizing old errors and not like actually being wrong, and it can kind of unlearn them. But yeah, so it's very important that this D0 is good. So
I do have some questions. If you so you say that you're training this model like for how long, or like what is the stopping criterion there?
Great question. They did not put because I'm just running the paper through my head. Did they list any? No. Nope. I don't recall. I remember in the paper they're saying they train on this union here, and then no, they don't have anything else on it. So the only point that they talk about any hyperparameters or anything like that is further on in the paper, where we're talking about like bigger pre-trained models, but they don't have any explicit actual like experimental formulation for when they stop training. Yeah.
Excellent. Next question. The size of all of these data sets is the same? Like for all DI is the same size, or it's a different? I can't really read what's the size. Like, is it NR? You denote it?
Well, actually, I have a question about the same thing. If you said DR is a superset of all the others, then isn't D1...
It's not.
Oh, never mind. I see the union's fine. Isn't it a superset though, you said? Like D1 contains D0. Oh, but you're... Okay. You can continue.
Yeah,
I guess it's not.
I think so. It doesn't matter
But,
even if it is.
okay, so the size of the sets, like, who decides the size of the sets and how is it set?
Actually, the D0 has the most, is the largest one. For reverse addition experiments, like for D0 could have like 2 million. And for each of the DR, we'll have like
so it's
50,000. That's kind of a ratio. And for each round, it will get a filtering filter the D0 and append the new DR.
Okay. And I guess another hyperparameter is going to be this D0 difficulty level, whatever difficulty is.
It's just for the way they're phrasing it, it's just the easiest problems they have. And then of course, what's the definition of easiest? But
yeah, because it could be single digit numbers, and good luck with generalizing them to multi-digit numbers from there.
Yeah, and I was gonna get into this later, but we're here now. One thing that I was kind of thinking of, and they kind of just skirted around, was it's really easy this difficulty function is paramount to this paper. So it's really easy to say the difficulty of like addition is just the number of units or the number of digits. But the actual proper function for difficulty for other problems, they just completely avoid, because like, I mean, to see how hard things are is hard. So, yeah, that's one thing that, not a gripe of the paper, but they kind of avoid that problem.
As in, they always measure the difficulty by the length.
Well, they give us, they use problems where it's easy to assign the difficulty, right? So, cause like for the maze solving, it's length of the amount of nodes and the length of the optimal solution.
Yeah.
So all the problems that they train on are just simple digit-based or simple mazes. There's not anything where the difficulty metric is at least slightly hard to find, is what I'm trying to get at here. Okay, are we good on that? Yes. Okay, so now we'll get into data filtering. So this is kind of like the important part to kind of remove the error from using our previous model. So there's two kinds of data filtering that we're gonna be using. So one is majority voting and one is just a simple length filtering. So I'll go over length filtering first. So right here, okay. So one point they made is, I don't know exactly how they came to this, but a lot of the times whenever the model generates incorrect results, it's because the generated label for the problem is too short. So because the model's been trained on shorter, easier problems, when it sees harder problems, it thinks that they should also have shorter solutions. So one easy way to kind of remove these short solutions, which just can't physically be true, is just by simple length filtering. So they actually made a nice diagram that I actually kind of quite liked. So they just arbitrary length of strings. This is literally just a complete arbitrary length. So this is all the resultant labels. What they do is they they call this L, which is just the max length of any of the labels that they find here. And then they have this tau value, which you just subtract tau. And then right here, this is just an L minus tau. And then any of the results that land within here are good. And then, sorry, these are too long, right? Anything shorter than predefined threshold? Yes. So just a reminder, this is on the like dr minus 1. So anything shorter than this gets removed. But that's not like removing the d0 and stuff. This is just on the new harder set. This is on our dr minus 1. So only in this case, these two strings would be kept in this data set here. Because what they're saying is, for a harder problem, if your answer is really short, it's probably wrong. If it's long, it's probably right.
And by removing, it means you have like, let's say 10,000 XIs, then you ran your model MR minus 1 on those 10,000, and then let's say it produced only 1,000 that were in that interval, then you end up with 1,000 data points you actually end up using.
Yeah, you end up with how many data points, and that's what, they don't talk about how they got this safe distance tau.
No, I'm fine with like that. I'm just saying like, there was, like DR is the already filtered version, just to clarify, or?
Yeah, like this is the only one that's like filtered. Then every single time we generate a new NR sample, we filter on this. So we train, I should say this then. I lied. Good catch, thank you. So 4 is filter. Filter DR, and then now we train.
Okay, so they become much smaller.
Yeah.
Okay.
Does tau depend on R?
No, their distance, from what I recall, is just, it was quite arbitrary.
Wait, how could it not depend on R?
Well, they didn't state that it depends on R. I think it should, but they didn't state that.
But then I mean, like, until like R gets big enough, I wouldn't include any examples, you know? Like if that interval's like 100 to 200 and I'm multiplying 2-digit numbers.
Yep. Yeah. Okay, so.
I mean, they probably made some sensible choices that
Yeah.
depends on our.
Yeah, I would agree with that. Okay, so then yeah, so this is our length filtering, and then we also have our majority voting. And then, kind of not really big surprise what majority voting is they run, in this case, they run 5 models that are like seeded differently initially, and then they run them in tandem, and then if 4 out of the 5 of them agree on the label, it's good. If it isn't, it's out. So
Wait, so it's actually, they never train a single model, that they actually train 5 models.
Yeah, so
Are they training the 5 models with the new data then? So whenever you said that, oh, we are training a model, we are actually training 5 models.
yeah, so in this case for it was the addition ones that they.
I think the trained model with the same framework, same data set, just different random seed.
But so
Yeah.
they
But it's like 5 times the effort.
yes, so they only do this 5 times the effort one. They only do this majority voting on the harder problems. So for the string addition and stuff, they choose not to. But yes, you do make the problem 5 times harder by training them in tandem. Yeah. But they do that for the harder problems to be able to do majority voting.
So when they report the results later on, I guess
Sorry, say
about
again.
it. When they are reporting the results later, there will be some results. Do they use all the 5 models and majority voting still?
Yeah, for when they
For the final results?
for when they display the final results on all the questions that they do the majority voting on, they display the best model. And then for the other ones, like for the string addition and stuff, they don't do majority voting. They just do length filtering, so they just display that model.
But okay, so basically they try to, with some procedure, select out of the 5 the best
Correct. Yes. Again,
first,
yeah.
and then they report for that model. Or like maybe it's just like they calculated the test error for all of them, and then they report the best test error for all the 5. That's a little bit.
That's the most sensible. Yeah.
No, I mean like that's not really a good practice, right? Because if I like this, like flipping the coins many times, then there will be some head.
Yeah. Yeah. It seemed that the length filtering was the largest source of like good filtering. The majority voting they just used on the harder problems. Yeah, but it also did result to a good change. It did help them out. Okay, so find that. Okay, so then you want to do results of the visit? Okay. So that's the definition.
Okay, so for clarification, I think the majority voting part, that's suppose they have like 5 models, they will run the same case like 5 times until they get like a 4 out of 5, and they take this as a final result. Yeah, so they kind of use this kind of majority voting to guarantee the self-generated data accuracy. Okay, so next I'm going to give you some specific example on task.
Erase whatever you want.
Okay, erase here. Okay, so first task is about the reverse addition, and I'll just use this framework to get some details. Like for D0, they will have add some parameters and for the difficulty they will have they will have a digit from 1 to 16. And they totally have like 2 million samples for training, and they train for okay. So suppose this is D1. So for the D0, so for the D1, the end digit will be equals to 7 and 7 only. And this kind of this subset will have like a short, smaller size. And then they will combine the D1 with D0 and for the next step training. And with this kind of framework, so the D2 will have an 18 digit. And in the end, they will have a result like Like we mentioned, that this paper is mostly empirical paper, so they conduct most of conclusion we get from the real experiment. Like for it's kind of a result that the x-axis is a number of digits and the y-axis is the accuracy. So here's it's 1.0. So at the beginning, they got a 100% accuracy on the original training set. This is round 0, and for the round 1, they will get a little bit. Will get a little bit of progress, so that they can achieve accuracy to be 0 at digit 17, and for all the rest, they will have the same trend.
But these the curves measured on additional examples that were not in the training set.
New rounds.
It's a kind of new round, like adding the new data set and training result.
So these are curves generated on the training data.
Correct, yeah.
Yeah.
Each curve represents a step forward in difficulty and the responding accuracy of the model when it's seen that step
Yeah,
forward.
but
in difficulty.
I am asking the question, how do you get a point on the curve?
I think
What's the calculation?
I think the accuracy should be on the testing set. Yeah, they just it's kind of a testing result after each round.
Okay.
So they have a separate data set to check?
Sorry?
Like they have a separate D1,
Separate D1.
which is a D1 test?
It's like for the first round they got D1, but for the second round they got D2 for the training.
Well, I
And
guess what
D1
Trev was asking is, D1 is going to be used to train the model, but is there a D1 test on which we evaluate?
They don't explicitly state any of that.
Yeah, but
Yes,
I
sir.
think the D1 will also be included in the training set, so the testing set will be also used, I guess.
Huh?
I think the testing set, like for each of digit, they will have a test set, and then test the train model on the test set every time.
Okay, so there is a D1 test,
Yeah,
and a D2 test, and a D3 test.
yeah, you got each digit they will have a
And
test.
even a D0,
the
wait,
same one, no?
is there a D0 test? Like when you get 100% accuracy, is that on all the points in the D0, or is it on new data?
I think it should be on the test set of 1 to 16 digit.
Okay,
I mean,
that's pretty
it
good.
doesn't make sense that they get the result on the training set.
Well, I don't know. People do it.
I think this is kind of from D0, D1 to DR, they're all about the training set. But the testing result, it should be on the test set. So I think with kind of a framework, they can always get to like a generalization on 100 digit. Okay, and it's kind of a result similar applied to different tasks like string copy and string reverse.
So this is like after all the filtering and everything, you really get 100% accuracy doing this thing at 100 digits.
Yeah, something like that. Yeah.
Every single one of the problems showcased graphs like that of
Yeah.
slow, steady growth.
Yeah.
And the amazing thing is that you never had true labels for anything after 16
Yeah,
digits here.
yeah. You don't have a true. Yeah, only the D0 is guaranteed correctly.
Yeah.
Yeah.
Do they give any rationale why 16? Is that what worked for him?
Just starts there.
Just use it.
I mean, even on the training set, this would be impressive.
Okay. It's kind of why they use this training framework. And yeah.
You can just do that.
Sorry, if they layer on the training set, does that mean that they are kind of measuring the representability of the problem or something like that? If they reach to 100% in the training set,
Yeah.
that means that I don't know, the transformer that they are using is kind of representable enough.
Yeah, it seems as if on these problems, yes, there is that
So I mean,
representative.
yeah.
Oh yeah, what are they training? Like, is it a transformer? How big is it?
Transformer,
Transformer-based model.
they'll later
Is
on.
it always the same size?
Later on, they talk about the types of transformers, and then so the transformers that they're using in this initial plate, they don't give us a lot of information on. Later on in the paper, they talk about pre-trained transformers, and they do compare results of larger sizes transformers, which we'll get to. They talk about changes of sizes in the transformers.
Yeah, I think it's kind of just prototype of for the model, and I think they kind of tried it on many different models,
Yeah.
like including Llama 3.
Yeah.
Yeah.
So one thing though is that if they don't continue training, it seems that the performance drops off.
Yeah.
So anytime you want better length generalization, you have to keep on training. It's not automatic that you get
Yeah.
Yeah.
They have
good
to
length
train.
generalization beyond the training data, despite the fact that somehow the self-generated labels are sufficient to continue performing well.
Yeah,
Yeah.
and
So it's
the,
kind of, yeah, it's really interesting. I guess like maybe it shows the role of data filtering and whatnot.
yeah, so one number I forgot to bring up is the accuracy of their hardest multiplication model. Their average accuracy without data filtering was 31%. With data filtering, it was like 95.3. So data filtering is hands down the only reason why you get this kind of very slow incremental results, because they show that without it, it just, the error avalanche is insane. It just plummets the performance.
But it's also interesting that like you would think that the model has a tendency to make certain errors at some lengths, and because of that data filtering is going to reject examples of the type on which you are making errors. So you can kind of end up in a situation where you have partial coverage for an increased range of lengths, because of the rejection built into the data filtering process. And despite this might be happening, somehow when you train on the slightly more difficult problem, the problems go away. Like on test accuracy is 100%.
Yeah, and
That's like filling in the gaps of the other model perfectly is possible, and that's really surprising to me.
yeah, and then when we get to the acceleration framework, it's going to be even more perplexing because they go further in difficulty. We'll get there.
Okay.
I think one thing is maybe to lead to some of the like surprisingness of this is just it's kind of hard to draw graphs. These drop downs aren't like incredibly aggressively like very fast. Like this value here would be like 19, 18 digits where it's down for. So there is a little bit of gap of digits in here where it does relatively well. It's not like this after you have 16 digits, if you try on 17 digits, it's 100% wrong. It does have some length of generalization.
Yeah.
Yeah.
And another thing, like I think within the paper, they only mentioned that they can achieve like a 100 digit, but for the longer one, they don't mention that. But I guess due to the model capability, I think they cannot do more than that. I mean, like.
But I still would go back to this observation that if you are only training for, I don't know, 20 digits, then on 30-digit numbers, your performance is still not good, despite the fact that you've been doing this for a long time. And so it seems that whatever the transformer learns, it doesn't quite learn the algorithm in a reliable fashion, ever. Except for the ranges that are covered. and maybe a little bit more, but like tiny little bit more, right?
100%, because like they can't claim that they're really helping this model generalize all that much. They're just helping the model generalize a few steps forward from its current
Yeah.
position of knowledge. So yes, that is kind of the funny thing about this, is the model isn't really generalizing. It's just generalizing a little bit ahead of what it knows.
Yeah, I think they cannot do it forever because the error will accumulate within
Yeah.
the training framework. So that's why they only said that it can only achieve the generalization until 100 digits, not to the longer one. So I think that's the upper bound of this model.
But you also wonder, like, it's almost amusing, like, I don't even know how I would hard code some algorithm that can only do well up to some length and then sucks a couple
Yeah.
digits later, and then it's like, somehow I improve the algorithm to do a little bit better, but not anything better, and then just constantly can keep doing this.
Yeah, it's
For addition, like, how did I learn addition? And every time you teach
Yeah.
me how to do it for a little bit more, I'm like, okay, I can't do better than that each time.
yeah.
Over and over again.
It's the model never learns. Well, there is one part of the appendix that where they ask, like, does it truly learn addition? But like, yeah, the model never really gets to a point where it learns the semantics of the problem. At least it
Yeah.
so looks like that, right?
Yeah.
Yeah.
Can I have a related question about this?
Mhm.
If you would need to set the weights for a transformer to represent the correct algorithm, how many layers would you need to solve this problem? Is it sufficient to have, like a small finite number of layers,
Yeah.
and you could solve the problem? Is that obvious?
I don't think
I don't
you mentioned
think it
the
is,
number
yeah.
of layer within the model.
Yeah.
Right. But I'm asking you, like, or maybe on Rasp, like, if you would want to write a Rasp code, and then we can think about like how to represent that using a transformer. How does that code look like? There is no chain of thought here. Like you have to kind of
Well, there's kind of chain of thought.
like you have the length of the input, and then you are
Okay.
output aggressively decoding, right?
I think
Uh,
I think the sample for the task is pretty simple. Like it's like to and get a result like they don't perform a chain of thought any intermediate thing for this task.
yeah.
So it's just the input is a number and it got an output, something like that.
Yeah. But go ahead, Roshan.
No, I was just saying, so the way that you would do this in Rust is, for example, you basically need for n-digit addition, you need n-digit addition with carries.
Yeah.
Right, and so like if you're thinking of binary addition, you basically need to, for every digit, you need to find the corresponding digit in the second arc, like the left side and the right side, and then you just need to introduce the extra token, which is like the carry symbol.
Yeah. Yeah. I'd say
So,
so.
so it seems like if you have position encoding, you should be able to do that. The only problem is because these digits are of different lengths, you kind of need to be clever in how you refer to like the corresponding digits in the two
In the-
Right. So you have to find somehow the boundaries, and then relative to the boundaries, it's kind of like if you think about it, like that's why the reverse addition is also going to be much easier for the transformer, because you are supposed to do the addition from the least significant digit to the most significant digit. So writing the output in the other order, it creates this problem which you have with the pitfalls of next token prediction paper, just like almost like a parity problem, that to calculate the first digit in the normal order of addition, you really have to solve the whole problem, and then need to write out the solution, and that has to be done without the use of any additional space inside the model. I suppose that for normal addition, like not reverse addition, the number of layers is going to need to scale with the number of digits. And that's going to create some problems. If you cannot write out intermediate results, if you could write out intermediate results, of course you could somehow write out the result in the reverse order and then reverse it. Yeah, it's like a truly weird limitation of transformers if you think about it. That well, they have to do everything in their head, and so doing multi-digit addition or not even talking about multiplication in the normal order in your head is like no one can like like no one does it.
But that's only because we keep asking it to output the number from most significant to least significant. If you just, like you said, if you just let it like output least significant to most significant,
pretty simple.
and then reverse it afterwards and write that
Exactly.
out, I think it can work.
So how many
Exactly.
layers did the model that they did experiments on? How many layers did they have?
They didn't say, the only thing they stated on model parameters and properties was when they talked about larger pre-trained models that they did this self-improvement framework on. So
I think they tried multiple different type of models, even including the pre-trained
I was
models.
just thinking that maybe if you're like, oh, it has 100 layers, and oh, look, it doesn't work after 100 digits.
that would be nice, yeah.
Wait, and this was on reverse edition, this picture?
They all share that, but yes, this
Yeah.
one was, but they all share that same.
Even in regular edition?
Yeah, it's
Yeah.
just, of course, it's not gonna be as aggressive. And then with like the maze solving, it looks like this, but, can I run this real quick? But your peak slowly decreases, so instead of having this, you then more have like this. You have good there, and then it kind of there. So like, there is a very slowly decreasing upper bound for the really hard problems. So, yeah, but they all share that kind of look.
Yeah, the trend is the same. Yeah.
So I think I just looked in the paper, they use 6 layers, 6 attention heads.
Where do you use section 3? Oh, okay, so that was, well, there's your answer.
What?
6 layers.
I missed it.
6 layers and 6 attention heads.
You hear that? For this, they use 6 layers and 6 attention heads for this self-improvement framework at the beginning.
Oh, llama architecture.
Yeah,
Ah,
yeah.
14 million parameters.
Sorry?
14 million parameters looking at the paper.
Yeah, is that where they start talking about the pre-trained models are always better? Because, yeah, they do talk more about the llama architecture when they start talking about, I guess I'll quickly state it, they come to the very obvious conclusion that the more parameters the model has, the better performance it has. So, yeah, there's this section where they say pre-trained is better. They compared a few different llama models, open source, and they just said that more parameters, it does lead us to be able to generalize up to a higher amount of digits. So they do make that observation. I don't know if that's an obvious observation, but I kind of feel like it kind of is. So, yeah. There's that pre-trained stuff. You want to go with more, please?
Yeah. Like we mentioned earlier, that they got like a specific format for the multiplication, like basically break down it into like multiple additions, something like that. So basically, they're still performing the addition. And here they mentioned another, like we can see as parameters. Which could be called a difficulty gap. Like we said, we need to improve the difficulty a bit by bit. So for the reverse addition or regular addition, we can perform like a 16 to 17. But for some other tasks, like for step 1, basically, they were trained on the D0, which is n by n multiplication, where n equals to 5, and they want to get the n plus 1 by n plus 1. But in this case, if they only add the like 6x6 samples, it doesn't work. Like it's like this increased difficulty is too large for the model to get a self-improvement. So they need to further break it down into like we want to get from n by n to n plus 1 by n plus 1. So they got to they need to do something like that. Firstly, they need to get like n plus 1 by m multiplication, and m should be from 1 to n plus 1.
So you need to have the number of digits.
Yeah.
The difficulty measure of.
Yeah, they are both a number of digits. So the So in this case, like for D0, they got 5 by 5, and for the D1, they will get 6 by 1 and 1 by 6. And for D2, they got 6 by 2, 2 by 6. And in the end, they can get to 6 by 6. So they kind of further break down this difficulty gap into something like that. And I think the problem is that they cannot quantify the difficulty. They can just get this gap by guessing and by conducting experiment. Okay, if this gap doesn't work, I'll break it down and run it again. That's kind of that's kind of idea within its experiment.
Sorry, can you explain that again? So in this case, the difficulty level, basically the problem is there are two difficulties, right? Like one for each digit, and you have like one for each operand.
Yeah, I think it's like if they do that, the problem will be too difficult for the original model, and the accuracy is pretty low, so they got too many errors within the like a DR.
What I mean is like, so is that like how do they order these difficulties? Like so, for example, if you got n and m, you can go from n plus 1 times m.
Yeah.
Or n times n plus 1. So
They just do simple addition of the two operands. So
Yeah,
this
it's
has
just a
difficulty like
number
seven.
of operands.
So that's why these two are in the exact same difficulty bucket, because if you add them
Yeah.
together.
But I guess Roshan would then say that 5 plus 5 is larger than 6 plus 1, so maybe D plus 1 is easier. Clearly not.
Yeah, I think
Yeah, they-
yeah, it's true. Like just about how they calculate the multiplication. Basically, the guys each digit of the second operand and multiplying by the first one. So that's why they got like multiple. They got multiple addition.
In this case, the m arbitrarily is 1 through n plus 1. You don't, in this case, you wouldn't have to start with m starting at 1, right? Because if you wanted this difficulty to be more like linear, and like so it isn't funny like that, you don't have to start with just 6 plus 1, right? You can start like a 6 plus 3 or okay, then you're getting closer, right?
And because of its format, like for 5 by 5, it could be like a 5 times addition. But actually for 1 by 6, it becomes 6 times addition. So in this framework, they consider that 6 times addition is a little bit more difficult than the 5 by 5. That's what I say.
So this kind of seems arbitrary, but I guess there is a strong constraint because when they do that filtering stuff, they're assuming that when you have smaller difficulty, that produces strictly smaller strings as outputs.
Yeah.
So that imposes like a constraint on how you can make up these difficulty numbers, right? So that the filtering still works.
Exactly,
Yeah.
right? Because you need to have that linear increase in the difficulty to be able to make that assumption about the length filtering and that stuff.
So the difficulty has to do with the length of the output strings. Like the output strings,
Yes.
so they're defining it in terms of input strings, but it also has to do with the length of the output strings.
Yes, because yeah, even in the maze solving case, your output string is just your optimal path, which is a length, right? So yeah, that's the only thing that makes me not as mad about them just throwing the difficulty function out there, not worrying about it as much. Because with most of your problems, you can just reduce it to your output length, and then you can kind of reverse the difficulty from there. But yeah, they do state that this difficulty function is kind of just a magic for these problems.
Yeah. And actually, it's got a different difficulty setup for different problem.
Yeah. Okay. I'll do self-improvement acceleration. Okay, so this is the interesting part. So they said, okay, this performance looks great, doesn't it? They want to do more. So they introduced a self-improvement acceleration framework, which is basically this, except when we make our harder samples here, instead of going one step of difficulty forward, we also add just a few 2-step forward or 3-step forward, just a very small amount of slightly harder problems. Now, they do state, how do you find how many problems? How far forward do you go? How far forward in difficulty do you go? What percentage of the data set? That's a very hard question to answer, but if they keep, it looks like if they keep running their experiments and play with those hyperparameters until they're happy, this is what they get. So this is the self-improvement acceleration framework. I want to make sure I get this right. So this is
what was this exactly? Like throwing a little bit harder problems, but like it's gonna be hand tuned of how many more of the further data sets we are throwing in, and like, yeah, that's it. It's like we had the data set D0, we generated D1
Yep.
based on the transformer we got on D0.
Yep.
We haven't generated yet D2, but we could use this initial transformer to try to generate examples from D2
Yeah.
Yeah.
using the same thing.
Yeah.
You do that, but then like once you did that, like how many of those you do include, and later on when you trained on this new one, the next transformer, are you going to generate more D1 type examples? Are you going to add those as well? Or you moving on to D3 and D4 level? Or how is it?
We will move to the D3 and D4. Because if we jump to the D2, then basically we skip the D1. So we will not cover D1 for the training set, but we will also test its performance. So basically we'll move to the
But
D3.
this just means that, okay, so if it was the way I described it, and then you seem to agree that that's what they do, then that would just mean that you kind of redefine what difficulty means, right?
Yeah.
Like that, like no, the buckets are a little bit bigger. That's it.
Yeah.
Yeah.
Yeah, that's true.
So
Is that right? Is that just what they're doing?
to my understanding of how I read it was when they increase the difficulty, they include within, so in like so when you increase the difficulty one step, you make that new data set, but within that difficulty level Z, there is some items within that are a Z plus 1 or a Z plus 2 difficulty. So that data set as a whole is majority difficulty Z, but there are elements within that data set that is Z plus 1, Z plus 2, or Z plus 3 difficulty.
So just in this example, your D1 had digits of length 17. Now it might have a couple that are like 18, 19, 20, right?
Yes.
D2, is it gonna have digits of length 18, or is it gonna start at digits of length 21 onwards? I guess.
18 is what that's how I read the paper, that's
Okay.
how I understand it.
So I guess that's different than what you're saying, Shaba.
Okay. That actually makes more sense then.
I'm pretty
Yeah,
sure it's
I
that way.
agree.
It's still an incremental level of difficulty. However, in that new data set, which is slightly harder, there are a very small amount of even harder problems.
Mhm.
But you still contain that
Yeah.
easier difficulty. So
But that's a little bit contradictory to that generalization thing. I mean, if you have a little bit harder.
Yeah,
so
exactly.
exactly. So that's exactly why in the paper they say it's incredibly. I don't know exactly what, but it's incredibly important to know exactly which harder examples to choose.
Yeah.
Which is kind of, well, if I knew which hard example is the easiest out of those harder ones, that's a pretty hard question to ask. But they just arbitrarily go, oh, okay, yes, we do have drastic performance afterwards,
Yeah.
but if we choose the right samples correctly, of course, this is an accuracy measure, you're still gonna have at 50% accuracy some correct results. So if they choose those ones correctly, they can do this acceleration. Does that make sense?
So basically, if the difficulty step is too large, then you could probably fail.
Yeah.
You can probably fail all the training. But if you get the proper difficulty step, and it could somehow get some acceleration for that. So it's difficult to choose it, and it's kind of choose for the difficulty step cannot be generalized to multiple tasks. So that's why I put it.
So,
already mentioned that. Yeah.
the results they gave were for both string copy and reverse, but they both show pretty similar results. So they don't do the self-improvement framework up until a certain n amount of rounds. In this case, it was 20. So obviously just to like support that, it learns something in the initial rounds, and then we only do this addition of slightly harder problems after a few rounds. So here we have the amount of rounds it's gone through, and this is like the length it can generalize like correctly, right? So how far forward can it go and it can still generalize? So if you keep doing the regular framework, it shows pretty decent progress linearly like that. But if you can magically somehow know which harder problems to choose, like much harder problems to choose, they got exponential acceleration. So they got something more that looked like this. Well, not that aggressive, but I wish. That would be nice if Transformers did that. But yeah, so what they said was if you are able to correctly quantify your like Z plus 2, Z plus 3, which one of those data sets to actually use to challenge your model, you can get some pretty fast acceleration. But again, that is off the basis of having the ability to actually choose which challenging problems to include.
What does the x-axis say, rounds?
Yeah, the amount of rounds that the model's gone through. So,
Oh, rounds.
yeah, sorry, like the rounds of
Yeah.
training of the self-improvement framework. How many self-improvement framework rounds
Yeah.
it's done. And then, yeah, so we see pretty linear growth with the, like the length it can actually generalize that. But if you magically include bigger and better ones, you have much faster growth.
But just to clarify, if we drew like the 20th round here or something, then you would be at D20,
Yeah.
let's say. And at D20, there's like a giant difference between the dotted and the solid line. But D40, or D20, yeah, D20 would have these like, that would be the 40th.
Let's
They
just
would
do
have
string copy, and that's just
a
strings of like
copy.
20.
Well, that has like, so yeah, if you look at round, like let's say 40,
Yeah.
I guess you'd have strings of length 40.
Correct.
And that's what the dotted line would have. It would have strings of length 40, 50% of the data would have that, and then the remaining is like uniformly sampled, whatever. But the fat line, or the solid line, it would have like a few examples of like length 41, 42, 43 or something, that's it? Or it would really have things that are like length 100, because that like...
It would have it would have, again, they don't exactly define how far forward they go. I would suppose to have a result such as this, your R40 is going to have results of like an R50 or like exactly as you're saying, but they don't say how they go and choose how far forward and how much of how far forward they choose, right? So again, you have exponential acceleration if you can make that distinction.
Yeah. So in other words, if you kind of decide on the right way to partition your difficulty, you can optimize over it or something.
Yeah, so that's why this difficulty function I kind of been focusing on so much, because it is the paramount part of this.
The other thing is that because you're kind of doing this bootstrapping thing where you're
Yeah.
using the machines to generate labels, there's a question of like how many wrong labels it will generate, and how many of those wrong labels get filtered out by the filter, right? So if you have a machine that generates whose mistakes are mostly that it's producing strings that are too short, then all of those mistakes are going to just like get removed by the filtering, right? That's like an interesting question of like, what kinds of mistakes do you make? Do you actually get the digits wrong, or do you just get the length of the sequence wrong?
Yeah, no, that's a great question. They did make an observation that a majority of the incorrect, so they call it OOD or out of distribution, the majority of incorrect OOD results were when the length was too short.
And that was true even with this acceleration.
Yeah, they said this for all of their problems. So yeah, it was pretty strong in the sense that like length is the biggest thing, which to me makes a lot of sense because of this graph. Because if as you go further in difficulty, your output should inherently also get longer. So if you're having results that are short, that seems a little wrong, right?
Yeah, but equivalently, because I'm going to define the difficulty to be the length of the output string, like you said.
Mhm.
So then we just forget about all these questions of what difficulty means. Difficulty is exactly the length of the correct output string.
Yeah.
And then you have, if you happen to have a problem where the transformer just happens to produce strings that are the wrong length. Like that's the only kind of mistake it makes. Then it's perfect, right? Like then you will get perfect bootstrapping because all of those mistakes will get filtered out.
Yeah, yes, the only thing on that is the difficulty gap. So just because your length goes up by like 1, in the case of multiplication, does not mean your difficulty linearly goes up by 1. For the copy, it does. You add a digit, it gets a digit harder. But if you add a digit of your output in your multiplication,
I mean, it just goes up by 2, right? Like the
Yeah,
length of
it's-
the output in multiplication is the sum of the lengths of the inputs. In addition, it is the max of the length of the inputs.
yeah,
So those are the only 2 functions we care about. It's either the sum or the max, at least for addition and multiplication.
yeah, sure.
There's a factor of 2, but mostly not.
Yeah. Let me check. All right, what do you want? Yeah, sure, do that. You can just erase my graph on here.
Like we already mentioned, that is this, except for D0, all the rest data set are the self-generated data. So
And one thing I should note that the paper makes note of, I don't know if I've said this before, but they cite literature and they show it themselves. Model collapse in the sense that like you just don't have any improvement of data is inevitable. The question is only when. So in the case here, my guess is their model collapse was somewhere around about here, and then they went, okay, we'll stop there. So that is one important thing about the self-improvement framework, it's not an infinite benefit. It's been proven, there is a point where your self-improvement framework is just gonna collapse. Yeah, so that's a very important part of this self-improvement framework.
yeah, and that's kind of a figure for we can call it the model collapse or the arrow avalanche. Like at the very beginning, for the first several rounds, you can get some matched accuracy, like this is current accuracy, and that's the next round accuracy. But at some point, they will get to drop down from this is a y equals to x, and it will get drop down a bit by bit. So when it goes to some point like that, and then I think the self-improvement training will have to stop. Like just like over there, like they can only get to the certain point. So actually this it kind of means like this arrow avalanche, or we can say the model collapse. It's kind of inevitable. It's just a matter of time. So basically, to my understanding, like so it's kind of a self-improvement training. It's basically trying to push the model from the current capability to its upper bound of the capability. So beyond this upper bound, beyond the limit, no matter how good your self-generated data is, it doesn't work. It just cannot do it. So that's why we got a lot of intermediate mechanism like data filtering or majority voting or like some correction mechanism. All of them is trying to guarantee the quality of the self-generated data, so it can somehow postpone this arrow avalanche happens.
I don't understand the thought. What are the points?
It's kind of this is a y equals to x. So as a first round, if suppose like a round 0, round 1, round 1, round 2, this is the current round accuracy, and this is the next round. So for the round 1, it means like round 1 you got accuracy equals to 0, equal to 1. So and round 2 accuracy is also 1 if it's on this line.
So basically this is trying to get at the model collapse.
Yeah.
So it's just trying to show those arrows there are trying to show a trend that even if your current round accuracy is all right, after a certain amount of intervals, your next round accuracy is pretty far down on the y-axis there, right? Even though you're halfway through the x-axis.
Yeah.
So that's the point we're trying to get.
So suppose for this point, like your next round accuracy is lower than your current round accuracy, which means that it start to get some degradation on performance. And this process will go through to something like that.
Oh, I see. So you start at the top.
Yeah.
Yeah.
And then at some point, and then so there's the arrows are representing like a third axis of time.
Yes.
Yeah.
Exactly.
Oh, I see.
Okay, so one thing I have left here. Okay, so a little bit more on the model collapse there. So just a quick little extra point there. So they did make a framework to kind of like inject errors and see how far you can push it. And they made this conclusion. I also cited another paper that made this conclusion. I found it quite funny how they worded it. So they say that for model collapse to happen, it's not false memorization of like incorrect problems. Well, that's a part of it, of course, but it's false memorizations plus spurious correlations. Spurious correlations. So for model collapse to happen, you have to have both this, I made a big note of this, and memorization of data. So this was a point that they tried to drive home, is these models don't collapse just because there's like one or two or a few incorrect labels generated here. There needs to be that plus a spurious correlation of the data.
Which means?
Great question. They say that that's what has to occur. I don't understand either.
Did they say what model collapse is?
Like the model collapse?
Yeah.
The model collapse is just like your next training accuracy, you're not self-improving. So even if you're giving it like a Z+1 difficulty, it's not learning Z+1 at all. Yeah, so that's the memorization of incorrect results.
Yeah,
And
it
then this-
could be like the figure over of the right side.
Yeah. Okay. So yeah, and then in an ablation study thing, they kind of talk about, they don't do anything empirical to it, but they talk about how important it is to very slowly increase the difficulty. So obviously for this result here, we're seeing that. But yeah, they make a key point that this self-improvement framework, especially the self-improvement acceleration framework, only works on if you increase the difficulty like really slowly. So you have to increase the difficulty really slowly and only give it a little bit of like harder problems. Otherwise, it's not happy. So yeah. Okay, that's all I have.
Yeah.
Okay. Yeah, like I said, this is an empirical paper, so no more scary theory. You guys got freed. Any questions, comments on this? Because yeah, that's kind of what we have. This paper was just talking about the self-improvement framework, moved over to air avalanche, and then moved over to our acceleration framework.
What year is it from?
25.
What was it like, I still don't understand, like, it's just claiming that this is like a good strategy to get better length generalization if you're just to train, I guess, without this strategy on D0 to begin, because you only have D0, I guess, to start with.
Yeah, you only have the truth of the D0,
Yeah.
like these are with the labels. So yeah,
Yeah.
what this paper is, the spark notes of this paper, what I get is, if you have a problem and you have a quantifiable way to identify the difficulty, you can, up to a certain arbitrary length, increase your difficulty and then increase the generalization ability of the transformer. So that's what it seems like. It seems like if you only have a transformer that can do well on this difficulty, this framework works great, because as long as you can keep slowly giving it harder problems, it works. So that's what I got out of it.
And you come up with some clever filtering.
Yeah, I'm pretty sure the filtering, both weren't by them. So they were just cited by other people, but.
I mean, like, an alternative thing is, like, in a lot of math problems, you can just verify whether the answer is right or wrong. Just discard all the ones that are wrong, and you're always gonna have good labels.
That was my question. Like, if we try to do kind of similar thing, but the labels are generated based on truths, we know how to implement these algorithms. How would those results look like compared to this?
Yeah, because I think you're kind of getting at, like, it's easy to verify the answer, and then, because in this case, when they generate.
Then like why, yeah.
Like.
No, not even verify, generate the answer. We know how to generate the answer to addition or whatnot, like all of these problems.
Yeah.
So we can generate training data on more and more difficult problems. This is not a problem. do the results improve? How would they look like? I mean, okay, I actually look now at the appendix. In the appendix, they also talk about whether the models actually learn the algorithm. And then you can suspect that they don't, right? Because from these graphs as well, it seems that, well, they didn't learn because then they would generalize to any number of digits. And lo and behold, in the appendix, if you look at, like they looked at test cases where the number of carries in the case of addition is kind of controlled. Like you have 1 carry, 2 carry, I don't know, up to 20 carries for 20 digit numbers. And as you expect, for forward addition, normal order addition, the performance drops quite a bit. If the number of carries is, I don't know, if they were training up to 10 digits or something like that. If the number of queries is more than 4, then it's already not 100%. And then it drops. For reverse addition, it's better, but it's not 100%. So this kind of just says that, okay, it didn't learn the algorithm. So one question is it because it was just done with self-improvement, or it would still not have learned if we got all the labels all the time correct?
Yeah, no, that's interesting question. Because I definitely think this paper, because it's very easy for us at least, for like the addition things, because they do this data filtering. It's unsupervised data filtering, right? It's simple for us to do like the supervised, to be like, okay, this label's correct or incorrect in these problems because we're dealing with addition. But I think the goal was this simple problem. If they have other problems which it isn't as simple, they can use these unsupervised data filtering techniques to, at least at best, try to have that be as good as possible.
But I guess they never compared to the cases where the data in the different rounds have correct labels, just to see how that differs.
Yeah, they never do like a for sure verified set of all the.
Yeah.
I guess the motivation for this paper is slightly different. It's like the community somehow got into this idea of self-improvement business, and people were saying, oh, but self-improvement doesn't work, and then this guy just want to say, oh no, self-improvement, you can make it work if you are a little bit more careful with it, right? Is that correct?
Yeah, no, I would 100% agree with that. This paper reads as a, look, we can do this level of self-improvement given these techniques.
Despite what other people said earlier.
Yeah, probably. But yeah, the really key important thing is the data filtering. So these two techniques they used, of course, aren't the only two ones. They don't mention other ones. Yeah. But I would be very curious to see what other data filtering techniques there are, especially in problems where it isn't as easy to go, okay, obviously 1 + 1 is 2. Like, it's for problems where the filtering the data is actually of quite high paramount. It would be interesting to see.
But what I was arguing is there's a lot of problems where verifying isn't that hard.
Yeah.
But getting the right answer is hard.
Yeah.
And so you can just filter with a verifier that you have. And then as long as your model generates like, I don't know, 10% of the time it's correct, you can get a bunch of data points.
Because in theory you're...
But then I guess you get bias to the type of things that your model is correct on, and then maybe that causes problems. But
yeah, because I mean...
To me, what's a little bit disheartening though is that, well, they still don't learn the correct targets.
Yeah.
Yeah, because it would be nice if these curves were like this, and eventually they would have curves starting to like actually flatten out, right? And then having a generalization. Exactly. But they don't.
Or like it increases the range. It seems like it drops out kind of at the same pace, regardless of the length, which is also very, which kind of tells you that it learns something, but it learns very differently than learning the algorithm. Yeah. It miraculously avoids picking up the algorithm, and yet kind of solves the problem up to the number of digits that it was presented with on distribution or something like that.
Yeah, they're kind of showing that this transformer, in the sense, doesn't have to actually truly learn addition. Well, it would be nice if it did, but it doesn't have to. As long as we can give it harder and harder problems, it can learn addition up until that point. So if we have a data set where that's kind of the difficulty that we only care about up to that point, then this self-improvement framework is quite advantageous.
But actually it doesn't learn it, right? Like in the appendix, there is that section that talks about if we are testing it more seriously, then we see that there are errors.
Yeah.
So it's like it's
Doesn't
like
learn
it's,
the
it's
algorithm.
masterfully avoiding learning the right.
It's actually more scary than the theory would have been. Like the fact that you can think a transformer has learned addition, but actually it's not learned addition. That's a new fear that's been unlocked in any, like whenever you're reading any empirical paper, right?
That is actually, yeah, that does kind of unlock fear. Yeah, you think it, because I mean, looking at this, like looking at this one, you'd be like, oh, look, it's
Yeah.
learned addition, but then it ain't.
It's kind of amazing. Can you imagine a human that like you keep giving them a slightly harder problem, and like after 100 steps of you're teaching this kid, it's like
No
if they can add 100-digit numbers and they still can't add 101-digit numbers. Like, come on.
Yeah.
It's like, so I guess John said that recently, but it's like the Chinese room argument, except that the room doesn't contain the algorithm for addition, it just contains like tables for longer and longer numbers.
Yeah, yeah.
But also I was curious, so what other problems did they have besides addition and multiplication?
So they had, so their addition, they had the reverse addition, they had string copy, string reverse, multiplication, and maze solving. So maze solving and multiplication were the ones where they kind of had to deal with the difficulty gap, and those were the harder ones where majority voting was required for the model to not collapse instantly, where all the other ones, they had length filtering, and that's it. Anything else? All right,
Alright.
school's out.
It's an early finish
Okay.
today.
I told
Yeah.
you guys this we would do it on time.
Yeah. Thank you guys.